Hi, I'm Kate, I'm Big Kate, I'm your herald. The way this is planned to run is we're going to introduce the speakers here. We're going to have a Q&A session at the end, and the plan is that if we run out of time for everyone to move from this space over to Wireless World, where they're running tech demos on site, and you can just carry on from there, okay? Right, this is, let's go through from the top. This man here is Eric Blossom. Eric is a 20-year veteran of wireless design. He previously built the Starium 100 telephone security system. And the key point here is he's the founder and leading light of GNU Radio. On his left.
Wow! Nobody's throwing their underwear.
You're hot.
Yet.
You're hot.
I know.
On the left is Mark Ettis.
Matt.
Ettis?
Matt Ettis, yes.
Matthew Ettis. I do apologize. Matthew Ettis. He is the founder of Ettis Research. He's worked in wireless design for 9 years. Has extensive experience in ASIC design, FPGA. For those who don't know, it's field programmable gate arrays. He built and designed the universal software radio peripheral, and that retails about $700, or because we're in Europe, 700 euros.
500. Yeah.
For those of you who don't know, just a quick introduction, because I really don't know much about GNU Radio, so this is new for me. GNU Radio is a free software toolkit.
Oh, you're stealing my slides.
Sorry. GNU Radio is a free software toolkit
GNU
for
Radio
learning.
is
Sorry.
a free
Sorry. Sorry. I apologize.
Yay! It's okay, really. We'll do great.
I'm used to shouting to the whole room, you know?
Yeah.
It's for learning about building, deploying, and, you know, general software for getting the software to work. Sorry about this. It generally is considered to run best on the universal software radio peripheral, built by Mark,
Matt.
which is a small FPGA baseboard, which creates software radios. And there's a whole bunch of various add-ons for that. And I'm sure they're going to tell you a lot more about it, because I'm completely at a mystery at this point.
Okay.
And I'll be around to do the Q&A later, and what will happen is that you guys ask your question, and I'll probably repeat it, and then we hopefully people can understand what I'm talking about. Bye.
Okay, thank you. All right. Welcome. Thanks for being here. So who has actually used GNU Radio here? Just so we know who we're talking to. Okay, good. And who has seen some talk in the past about GNU Radio? Okay, good. All right. So Matt and I are going to kind of split the talk. Boy, that echo is a little weird. Okay, we're going to split the time up in the talking. I'm going to start with the GNU Radio part, and we'll give sort of the brief overview, and then talk about some of the things that are currently already working, and then the direction we're headed. And Matt's going to do likewise with Universal Software Radio Peripheral. And also afterwards, after the talk's done, we're in the big green tent in the wireless village. We'll do some demos. So we'll have people can gather around. We can show you what's actually happening. So as Big Kate said, it's a free software toolkit. It's really like, it's a big like foundation. You can, if you're clever enough, you could build pretty much any real-time signal processing system. Mostly we build radios, and what we mean by radio is anything having to do with RF. So this would be your regular kind of handy-talkie, walkie-talkie thing. It also could be garage door opener, but it could also be like a network for moving data, as well as like cellular thing or radar. So we mean radio in the broadest definition. I guess that's it. The key is it's under the GPL, and it's no news to this group, but it's a big community effort. There's about 1,000 people on the mailing list, and of course the number of active developers varies depending on the phase of Moon. But there's quite a few people, both sort of traditional hackers as well as a lot of academic users, plus some people from industry or various research labs. Okay, this is the canonical software radio block diagram. The idea is that you have antenna, some kind of a front end, and this is the transmitter. This is your code, the DAC, the digital to analog converter. Some way we got to get samples up to the antenna. And on the receive path, it's just the inverse. So analog to digital converter, and then into your code. So this code could be running in a field programmable gate array or a general purpose processor or some not so general purpose processor. Some people build them out of DSPs. We tend to focus on the general purpose processor, and then some of the code runs in a field programmable gate array. Fundamentally, when we started with GNU Radio, we had this idea that it was a data flow architecture, and that you had signal processing blocks that would do a particular operation. I mean, it could be very simple like add, but usually it's a higher level operation like do a kind of demodulation. And you wired these things together, so they have a particular set of types, and you can wire them together and kind of build this radio out of like little Legos that are wired up. Right now it's currently in C++ and Python, which we really have liked. It means that you can do your performance critical code that's actually executing at runtime and doing all the math is in C++, but you can string it all together with Python, which, you know, it's about 1/5 the number of lines of code you have to write to get the job done. We also have coming in our 3.2 release, which is our second feature release downstream, we'll be able to do all C++. We have some embedded systems developers that are wanting a smaller, sort of a smaller package, easier to deploy. So in the future, we'll be able to do all C++ for those who want to do that. And the platforms we run under, the GNU Linux, the NetBSD, we've got some patches for FreeBSD, OS X, and we have some support under MinGW and Cygwin. So to give you an idea of what GNU Radio looks like, I'll give you our version of Hello World, which looks like this. And what it does is it basically produces a sound out of your sound card on your PC that sounds like dial tone. This case is the North American dial tone. And the point is you just there's a sine wave at 350 hertz, another one at 440 hertz. So I create these. I've got this sync, which is where they're going to go to, which is my sound card. And then I just say connect them up. Connect source 0 to the 0th input of the destination and the other side to this. And I just say run. And that thing will run forever. And if we could show it to you in the tent, it's not very exciting, but that's a complete GNU Radio program. Now, it's actually Python, and we just import, from GNU Radio, import GR, which is the guts of everything. And then we say import the appropriate audio module, depending on your operating system and whether you like OSS or ALSA or Port Audio or Jack or whatever. Okay? This is what it really looks like with some, Python command line handling. So we've got these blocks. The blocks have a set of input streams and output stream. Some of them have like a 0 inputs and only produce an output. That, for example, could be something that like reads from a file, like you got a test case you want to read out of a file and just play back. Or if you're recording information, or a lot of times what we'll use it for is we have syncs where we'll write to file like intermediate results in a radio, kind of like what's happening in this stage, what's happening in this stage. We can, if you start thinking about signal processing, there's some very common cases where you have a block that runs at a fixed rate, that its input and its output are matched either 1-to-1, like I consume one sample, produce one sample, or I could be decimating, where I like consume 10, I eat 10 samples to produce one, or the interpolating, the flip case. And we also handle the variable rate, which is really handy for doing things like variable rate encoding, or there's sometimes when we're we're watching a data stream on the air, but there's like only packets occur every now and then. So, we only produce output when there's a packet there. This kind of who's using GNU Radio. I mean, probably our biggest group of users right now are academic researchers. There's lots of people both in the US and in Europe, as well as some other places that are, lots of people are using GNU Radio mostly in wireless networking experiments and in cognitive radio. We got industry people, DARPA, sort of a bunch of other government research groups, of course hackers, which is kind of where we started. There are amateur radio people and radio astronomers. So we have a couple of radio astronomers who post these great things to our mailing list that says, look, I know most of you aren't radio astronomers, but let me show you this really cool thing. And these people have built the home radio astronomy observatory. And they're like, oh, this is the black hole at the center of the galaxy. We're like, great, really good. It's kind of like, the other, just a sort of an anecdote, is sort of general strangeness. You think you're building something, and then the radio astronomy guy, he can walk in front of his antenna and detect the black body radiation from your body that's in the 2.4 gigahertz band. So you think about, you've seen the charts and the black body radiator, the big tail. Well, I normally don't relate like that I'm radiating microwave radiation, but in fact we are. And if you can see it, I'm like, wow. Who ever knew? What are we doing? What are people doing with GNU Radio? Sort of transceivers, transmitters and receivers. The wireless networking people, a lot of work in that area. Ad hoc networks, kind of a thing. There's some work being done in space-time adaptive processing, or this adaptive beamforming, where you basically want multiple antennas and you do a lot of math, and you can either see things or get better resolution or transmit in a better direction. Cognitive radio I'll talk about in the next slide. Radar, both passive and active. I got a slide on this later. Geolocation is that's when you're finding out where somebody's transmitting from. SIGINT, that's the intercept business. And the latest edition, I said, Matt, is there anything missing? He says, oh, muskrat tracking. This is like a rodent up in New York or something, right? Upstate New York, they got little wireless collars on them, and somehow there's a GNU radio tied in there somehow. So cognitive radio, no, it was not. Cognitive radio is, from the academic and sort of government research point of view, one of the really big areas of research in general with wireless networking. This is the idea that you have a very flexible radio system, a software radio, and then the question is, what if the radio could adapt on the fly to the changing conditions? So it could be the changing conditions in the RF spectrum. It could be changing conditions like your location. Am I rural? Am I urban? It could be changing conditions like what policy is currently in effect, like what country am I in? We have different, we have the FCC. You guys have your PTTs or whatever. So you could think about this whole kind of multidimensional space. And the idea is that you would sort of the ideal situation is that these radios find themselves and optimize their communications. There's a lot of interest in this from a regulatory point of view, because traditionally radio spectrum allocation has been split up into little bands. Here's television, here's some television channels. Well, but here's radio, here's some radio channels. Here's cellular, here's some cellular channels. And this would allow people to just look around and see, is there unused spectrum, and then can we just use that for a while until somebody else shows up. These are some of the players using it, some universities. And for those of you in the wired networking world, there's a lot of people using it with this click modular router, which came out of MIT. Kind of a low-level details for those of you who know something about radio. This is what's working now. These are the kind of modulations and demodulations we can do. It's a orthogonal frequency division multiplexing. This is, it's sort of everybody's popular waveform today. It's what your 802.11a and G are built on top of. The DAB stuff is that way. bunches of them. FSK, GMSK, PSK, QAM. ATSC is the US digital television standard. And we got some stuff coming in the future, kind of depending on people's interest, which is fast frequency hopping, as well as the direct sequence spread spectrum. There's a new extension to GNU Radio that's kind of currently in the alpha testing stage, is this idea for message blocks. We've been at this for several years now, and one of the things we noticed is that the data flow abstraction works really well for some physical layer stuff. But then you have a situation where you have a lot of either control plane information, or you have packet-based data where you really want to attach a set of attributes to a packet. And you say, hey, radio, can you transmit this using a particular modulation scheme or a particular amount of power? Or maybe there's like some annotations, like if you have a steerable antenna, please steer the antenna 100 microseconds prior to transmitting the packet. So we basically have this annotations on the side. Also support for doing really precise timing, which allowed you to do time division, multiple access waveforms, kind of things where you got slotted things, or where there's real tight, you got to do something and get a response back. And it's all going to work with the classic GNU radio all strung together. I'm going to show you a couple of interesting things. This is kind of crazy things people have done with GNU radio, and this is my latest favorite, and I thought this is good for this crowd, which is, speaking of drones, this is about a 3-meter wingspan little airplane, kind of like a big model airplane, or looks like a little Cessna 172 that's all shrunk down to about 3 meters across. And what people are doing with this is building a synthetic aperture radar system. So it's an active radar system that can image what it flies over. It flies at about a kilometer high off the ground, and it's the neat part is it's built out of one of these universal software radio peripherals that Matt's going to talk about in a minute. A regular, just low-cost single-board computer, off-the-shelf 3-watt, Wi-Fi amplifier. And they managed to build a whole radar system out of this thing. So it's a lot, this is the $5,000 solution, including, not the $500,000 solution. So probably more than anybody wants to know, but they're generating the radar chirps in the FPGA and blah, 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 blah. They come out, and then it listens, and it comes back, and it basically, there's just generating the chirps and storing them in the little airplane, and when the airplane gets back, they suck the data out of it, and then they do a lot of math to put this thing together. The other thing is they're flying this airplane in circles, which is not the usual straight across, and then the math is like for CAT scans or tomography, where you've got this redundant data because the airplane's flying in a circle. Anyway, neat stuff. Some direction on kind of where we're headed in the future here is that, Moore's Law has continuing, Moore's Law is what made software radio possible. Like 10 years ago, people would say software radio, you say, yeah, right, how are you going to do that? 5 years ago, it started to become possible. Now it's getting insanely interesting in that we've got, you've got the multi-core, all of a sudden you can buy your quad-core Xeons. Or you got the Berkeley people who are saying, well, what we really need to do is start designing for 1,000 processor systems. Because your whole software paradigm is going to change. You can kind of go to 4 to 8 to 16, but then what about 1,000? And, they want to do that because they believe they can make that hardware to continue to scale for performance, but it's got to be lots of parallelism. Other thing is you got your clusters or multi-computers, and also then we've got these heterogeneous machines arising. The current one that kind of is popular is the Cell broadband engine, which has a PowerPC core on it and then 8 of these synergistic processing units, which are basically these SIMD. They basically do really fast floating point arithmetic. More on that in a minute. And another sort of a thing got my eye on here is when we start looking at all these different platforms for doing the signal processing, you've got the general purpose processor, things like the Cell, which I'll show you in a minute, the graphics processors, and then the FPGA. And right now, when you write the code, they're really written in different styles. Some of them, they're in different languages. They got different set of constraints. And I would like to find some way that you have a high-level way that's implicitly parallel, so we can take advantage of all this parallelism, and it's probably functional. For those of you who aren't familiar with the cell, this is just, you could do like hours on this, but the thing to know is there's this PowerPC over here. It's kind of a very sort of medium lame PowerPC. And then there are 8 of these units that are designed to do single precision floating point really quickly. This is the processor that's in the Sony PlayStation 3, but it's also in these big blade servers that are being built by IBM and by Mercury. There's this big ring that connects everything together, and the ring, you can push about 170 gigabytes per second around that ring. And the memory interface is really quite high. You get like about 24 gigabytes a second to main memory. The thing can do about 200 gigaflops at peak, and we think we can do about 30 gigaflops sustained. So one of these things that's in a Sony PlayStation 3 is about roughly 8 to 10 PCs worth of floating point performance. And that's what pretty much all we do in software radio. So we're really excited about this. So pretty much when I get back to the States, then I start working on this stuff. This is about resources. So I'm going to hand off now to Matt. We'll do some actually, is there any questions right now? We'll do more Q&A at the end, but before I step down, any questions so far? All right, good. This is Matt. He's going to talk about the Universal Software Radio Peripheral and where that's going. Oh. Please stand by.
I think
all
the
right.
Mic's a little strong, getting all my breathing.
You just get used to the fact that it's echo, 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 echo.
Okay. Does everybody hear me? That's good. Okay. Okay. So the hard thing with software radio is that you have to get your samples in and out of the computer, and no matter how much you process them in the computer, there's no real place to plug an antenna into it. And so I guess it's about 5 years ago now, I recognized this problem and decided that I wanted to create some open hardware to allow us to really do interesting things with software radio and GNU radio in particular. And so I went about creating the USRP, or Universal Software Radio Peripheral. And actually at the camp 4 years ago, had the first prototypes of it here, and we're playing around with them, bringing them up, had just gotten them back. So in any case, the goals for the USRP design were first to be very low cost and to be open, so that we could have a lot of participation, especially in this community, and to share and all learn from it. It was collaboratively developed with an input from a large number of people all over the world. And to make it easier to use for a wide-ranging different applications in software radio, we wanted to have interchangeable RF sections that would allow us to plug on different modules for different frequency bands to make it more flexible. And things I was interested in were wide bandwidth and beamforming and MIMO solutions. MIMO is like 802.11n now, is the new 802.11 system that uses multiple antennas to get higher data rates through the same bandwidth. So the USRP as a whole kind of looks like this. You have a computer which connects to the actual USRP system over USB cable, and on the USRP motherboard you have a USB 2 controller chip which talks to an FPGA over a bidirectional bus, and then the FPGA for transmission will send data out to a digital to analog converter, which will then go to the RF section and out to the antenna. And on receive, the antenna comes in, the RF section processes it in analog, and then it's digitized again on the usurp motherboard in the A to D converters and comes back into the FPGA and would go back into the host computer. And in the usurp, there's actually 2 copies of this the RF section, A to D and D to A converter. So one FPGA, but 2 of these other sections. Yes? Is it too loud or too quiet? Yeah, you're getting my breath. Okay. Okay, much better. Thank you. Okay, so what goes on inside the FPGA? We have our bus interface that talks to the USB 2 controller. And that's how we get our samples in and out of the computer. What we usually typically send over the USB bus is raw samples. So on transmit, they would come in and we would go through an interpolator. An interpolator takes a lower sample rate and essentially interpolates the samples in between those so that you can have a higher sample rate. And then it comes out, it is digitally up-converted and sent to the D to A converter. And Cordic and CIC are just efficient algorithms for doing that in an FPGA. On the receive side, we do the same thing. We have a digital down converter, a decimator, and it goes into the bus interface. And then there's control of the whole system. And so that's basically what happens in the FPGA. And this is somewhat out of order, but to tell you what the usurp overall, actually, it would be best if I do the picture first. Okay. This is the usurp. And so the way this works here is the USB 2 connector that connects to your computer. This is power. This is the USB 2 interface chip. And so this communicates directly with the computer, and it has its own high-speed bus that talks to the FPGA. The FPGA in this case is an Altera Cyclone. And in here we do what I showed on the last slide, which was the digital up and down conversion and the decimation and interpolation, other filtering operations, timing control, that sort of thing. And then these connect to these 2 chips. Now each of these chips has a dual high-speed A to D and a dual high-speed D to A converter, plus a couple other functions. So this is kind of our analog codec. It takes digital to analog and analog to digital, and there's 2 of them. And each of them, so this one has 2 lines that go to this daughter board connector. This is for the receive side, this is for the transmit side up there, and on this side it's rotationally symmetric. So this is transmit and that's receive up there. And the idea is you would plug on an RF daughter board for your band of interest onto these connectors so that you can basically transmit or receive on your frequencies of interest. So the specs, we have the USB 2 interface, which in theory USB 2 is 480 megabits per second. In practice, we get a nice solid sustained 256 megabits per second, which works out to 32 megabytes per second. And if you're doing, assuming you're doing 8-bit samples, that gives you 32 mega samples per second, which gives you 16 megahertz of RF bandwidth. If you do 16-bit samples, which we typically do, that would give you 8 megahertz of RF bandwidth. So 8 megahertz or 16 megahertz of RF bandwidth in and out of the computer, real-time streaming all day long. We have 4 A to Ds and 4 D to As. The D to As are 128 megasamples, 14 bits, and the A to Ds are half the speed and 12-bit. And so, yeah, in the FPGA, we do these operations, and you can reprogram that. There's nothing non-volatile on the board, so every time you power it up, the host computer loads the FPGA code and the firmware onto the board. So there's no programmer systems you need, and there's no way to wedge the flash in a bad state or anything like that. So it's all sent over, it's bootstrapped over the USB. And you can put 2 TX and 2 RX daughter boards on it at a time. Okay, so daughter boards that are available, there's a whole family of daughter boards. There's the basic TX and basic RX. Those are mostly for experimentation if you have your own external RF section. And they can kind of be an interface to the IF. There's the LFRX and LFTX. This is useful for DC to 30 megahertz operation, and also if you have an IQ interface to your own RF section, you would use this. If you want to just receive from 50 to 860 megahertz, there's the TVRX, and the DBSRX is 800 meg to 2.4 gigs. So this covers TV, FM radio, two-way radio, ham radio stuff. This covers a lot of, well, it covers both the cell phone bands, for example, both the mobile phone bands, and DECT, as well as radio astronomy bands, a bunch of other interesting stuff. Then there's the transceiver daughter boards. There's the RFX 400, 900, 1200, 1800 for a variety of different bands. These are all transmit and receive. You can put 2 of these on the USERP at one time, and so kind of cover a wide range of frequencies. So new transceiver daughter boards coming late this year, which are going to replace some of the ones on the previous page. There's going to be a 50 megahertz to 1 gigahertz transceiver. Forget the Q numbers; those are wrong. That's Q4. The 800 delays, you know, those hardware guys. 800 meg to 2.2 gig transceiver. That'll be Q1 of next year, and the 2.4 gig, 5 gig dual band transceiver. This will enable kind of both Wi-Fi bands, for example. This will be Q1 of next year also. And they're all MIMO capable, meaning that they're capable of working with multiple antennas at the same time in a fully synchronous way, allowing you to do very interesting capacity increasing things. So what are people doing with the USERP and GNU radio usually? Well, we have multi-megabit per second GMSK, PSK, OFDM modulation systems, which is actually one of the demos we'll be showing you in the other, in the green tent in the wireless village if you come by after the talk. MAC layer development, spectrum occupancy, cognitive radio, passive radar. SIGINT comment, this is kind of the US military speak for listening in to people who don't want you listening to them. And they're actually using it pretty actively. So, but those tools are also available to us as hackers. GPS, there's lots of GPS stuff going on, and people are using it to track cell phone locations as well. More applications. Dynamic spectrum access, this kind of goes along with the cognitive radio. The idea being you can sense, okay, what's going on in a band, how can I communicate with the people who are already using it, or how can I avoid interfering with them, how can I avoid them interfering with me, and best make use of the spectrum resource, which is of course scarce. We have over-the-horizon ship tracking radar, public safety stuff, soldier in the field smart radios, soldier in a cave tracking Osama bin Laden radios, wildlife tracking. That's the muskrats. There's a guy in upstate New York who has the muskrats don't carry around USERPs and laptops. They have the transmitters, and they little tiny transmitters. And if you've ever seen like a wildlife show on TV, there's always a guy with a radio, with an antenna and earphones, and he's tracking, listening for the beeps. Well, this guy has a fixed network of USERPs set up with multiple antennas, and it just does beam forming, and it finds the location of the muskrats. And so you can actually go to his webpage and see where all the muskrats in the greater Ithaca area of New York are. It's a lot easier than walking around with the headphones and the antenna. Medical imaging, student research, radio astronomy, all sorts of things. People are using the USERP for a lot more interesting things than we ever would have thought. So there's a large user community. They're kind of all over the place. And not all of them are being used with GNU Radio, although the majority are used with GNU Radio. But you can develop your own software to go with it. So the USERP was developed, the start of the development was, I guess, 5 years ago now. And the first prototypes I had here 4 years ago. And now I have the first prototypes of the USERP 2 here, which is the next generation. So I guess I'm on a 4-year release cycle. And the USERP 2, the idea is that it's much higher bandwidth. It's gigabit Ethernet instead of USB 2. So that now allows a unidirectional, it allows a 3x improvement in bandwidth. If you account for the fact that gigabit Ethernet is full duplex, whereas USB is not, it gives you another factor of 2 in there in a bidirectional application. So that gives us 25 megahertz of RF bandwidth each way, assuming you're doing 16-bit samples. If you were to go to 8-bit samples, that would give you 50 megahertz of RF bandwidth in each direction. This is getting to the point where it's going to be hard for the computer to keep up with it, and it's no longer limited by the interface. This board also has a bigger FPGA, faster A to Ds, faster D to As, with higher precision, 14-bit and 16-bit instead of 12 and 14, and has some onboard SRAM and a high-speed expansion interface. A lot of these things are it's looking at the USERP 1 and saying, well, what is it that people have asked for, and where do we want to take this? And really, the thing most people request is the higher bandwidth and the ability to do more processing in the FPGA. So that's why we have a more powerful FPGA this time around. So this time, instead of being bootstrapped over the USB, since we don't have USB and it's hard to bootstrap over Ethernet, we configure everything with an SD card, like in your camera. So there's a little slot for the SD card. The master oscillator can be locked to a reference. We'll use the same daughter boards as the USERP 1, except we'll only hold one at a time instead of two, and we get around that by that limitation by the ability to link multiple USERP 2s together through this serial expansion. Hopefully, if we can keep the power low enough, we can do power over Ethernet. So you could just run one Cat5 cable to this thing, put it in the rafters, kind of in the drop ceiling, and deploy whole networks that way. And we'll be shipping in January. So this is the layout. I'll show a picture of the actual board next, but it's easier to see on the layout, everything. So this is all power supply down here. This is the FPGA. This is the RAM. This is the Ethernet MAC, Ethernet PHY chip, Ethernet interface, high-speed serial PHY, high-speed serial interface, which will actually be a serial attached SCSI cable, although not serial attached SCSI protocol. And then up here, this is the chip that reads off the SD card to program the FPGA at power up. This is the D to A converter, A to D converter. That's clocking stuff up there. So you can see it's a much more busy board. There's a lot of stuff going on in the system. Okay, this is an actual prototype. You can see the SD card in the upper left. The RAM and the daughter board connectors hold the same old daughter boards as the USERP 1. And other interesting things, so the FPGA is actually big enough we're going to have a full 32-bit RISC processor in there, fully open source core from Open Cores. If anybody's ever heard of it, it's like free software but for FPGAs. Got the gigabit Ethernet MAC from that also, but it's required a lot of work, which we'll be contributing back. So the idea with a high-speed serial link is that you can connect a bunch of USERP 2s together. You can connect 2 directly, or you can connect 4 of them through a passive hub. There's 4 differential signals in and out on the link. One is the high-speed data at 1.6 gigabit per second. One is a reference clock. One's a time sync, and then the last one is whatever you want it to be. And so if you wanted to do a multiple antenna system, you would need more than one USERP 2. You would have to have one for each antenna, and you can link them together again with that same serial link. But everything will be fully synchronous, just like on the USERP 1. And we use serial attached SCSI cabling. Next step after that is to have this so-called digital hub, where you can link multiple USERP 2s together instead of directly to each other to another board with an even more powerful FPGA, which will have a PowerPC and possibly a DSP, and it'll have really serious bandwidth back to the host computer with 10 gigabit Ethernet and or PCI Express. So now we're talking, 100 megahertz, 100 plus megahertz of RF bandwidth in and out of the computer, which is some, in all likelihood, more than you could deal with today, but certainly would make for an interesting application. And again, this is where you can find out more about it, and of course we'll be doing our demos in the big green tent in the wireless village. And actually the next talk after us is also GNU Radio and USERP related, so maybe we should do it after that. So actually, yeah, so I think we're going to stick around for the next talk, which is about a USERP application. Oh, there's a big gap. Okay, we'll go there, we'll be back. We'll be in both places. Anyway, stick around for the next talk too. It's should be interesting. Does anybody have any questions? In the back.
Sorry, can I just come back?
I'm sorry?
Sorry, can you just come back?
Non-radio daughter boards.
Who's talking? Who's talking? Who's talking?
Yeah, so the question was, are there any non-radio daughter boards, because this would make for good test equipment? And the answer is not exactly. A bunch of people have made their own daughter boards, since the whole, all the schematics and layouts and it's all open source. So so you can get it, and you can make your own daughter boards and all that sort of thing. There are some people who've done that, and you could do things like use the LFRX and LFTX, because those are essentially DC coupled analog signals. So the LFRX, LFTX have been used for things like network analyzers, analog network analyzers, not Ethernet network analyzers. A guy named Chuck Swiger has done that. So there have been some people doing that. That hasn't been a real focus for us. Anybody else?
Yeah, okay. I'm Tyrell. My call sign's KF4DLK. Are you guys hams?
Yep. N2MJI, and this is K7GNU.
Okay, 73. Good to meet you. I'm also here with press, but I have a question about, in regard to ham radio. This is a pretty powerful tool that's going to enable a lot of people to get on bands that they couldn't in the past because it's cost prohibitive. But how are you addressing, or have you thought about the digital aspect? Because I noticed you're doing the digital analog conversion, but what about pure digital radio? Just like ICOM, I think, is making a pure digital ham. You know what I'm talking about?
Are you referring to like the ICOM D-Stars?
Yes,
stuff?
exactly.
Okay, so yeah, so even in that you send actual analog signals out over the antenna. So right. This is certainly useful for that. We have things like the GMSK and FSK demos we have, for example, are data networking, digital networking over radio. So yeah, no one's built an actual D-Star implementation yet, but all the building blocks are there. You basically have to you just have to deal with the protocol of D-Stars, because all the modulation, demodulation is GMSK, and we already do that.
Proprietary codec.
Yeah, and a proprietary audio codec, but the D-Star isn't officially locked into that, just all the implementations use it.
One more thing, if I can. Is this going to be compatible with something like PSK or PSK Mail or something like that?
Yeah, you could. So PSK, like PSK31, is a ham radio mode of communication. And yes, you could do PSK31 with this. It's sort of, this is kind of like the big, the really, really big fly swatter for that, because PSK31 is about 30, or it's less than 100 hertz wide, and we're dealing with kind of 16 up to 16 megahertz wide signals. So it's a few orders of magnitude wider than you need, but yeah, it certainly is capable of that sort of thing. It has? Okay, yeah, so Martin tells me it has been done.
Any more questions? We've got plenty of time. Is there any more questions? Help.
Okay.
I'm not used to people having questions. Are you sure you've covered absolutely everything you could ever want to know?
Okay, so let's...
experts in front of you on this subject. For the next 10, 15 minutes, you could ask anything you want.
Okay, so here's what we'd like to do. There's 45 minutes till the next talk starts, and that talk has also got a GNU radio component to it, and it's got cellular hacking connected to it. But what we'd like to do now is invite everybody over to the green wireless tent, and we'll show you some stuff actually working on the air, and we'll answer any other questions you don't want to ask in front of a big crowd or anything like that, and then we'll come back here after we do that for the next talk. So thank you very much, and we'll be here all week.